Okay, this video was requested by a student or one of your classmates. We're looking at sapling homework number 17, question number 5. Just be aware this may not be your question number 5 because it might be an algorithmic question, meaning there could be a bunch of different answers in there. So let's go through and process how we should approach this. Where we should start all problems is starting with the substrate. So our substrate, which I believe in lecture I was showing in blue, so we'll try and keep that, is this species. You'll notice that there might be a little bit of a weird thing there with that D. What does the D stand for? The D equals, I think I spelled this right. Okay, maybe not. Deuterium. Deuterium. It's just a way for us to ask a substitution question without changing the substrate classification. So deuterium is equivalent to hydrogen, but it is by definition different than hydrogen because it has an extra neutron, which means we can have a stereocenter at that position. Okay? But what it won't change is whether that is primary, secondary, or tertiary. So to determine that, I believe our leaving group I've been showing in purple. Our leaving group will be our bromine, so we want to classify the carbon where our bromine is attached. That carbon has only one carbon attached to it, so we are looking at a primary bromide structure. When we're looking at a primary alkyl halide, that would suggest SN2 chemistry. Okay, so at this point I don't have to read any of the rest of the question. I'm running under the SN2 mechanism. Okay, there is the possibility to run the elimination, or the E2, but we're going to see very, very small amounts of that potentially happening. We'd have to add probably a crap ton of heat. It's not a very good mechanism to run. So based on the substrate alone, we are doing the SN2 mechanism because we have a primary alkyl halide, sterically unhindered. Because we're running the SN2, that means we're running backside attack. Okay? Which means our nucleophile must come in from the backside of that structure, or the backside of our bromine, which will be down here. So this will be our nucleophile's attack, okay, coming in from that immediate backside. So what is our nucleophile? So our nucleophile is somewhere, it's going to be that species. So we can pull that down. Because we've already established that we're running SN2, we know this is strong, but let's work through it anyway. We have sodium and OCH3. Sodium is a metal, and oxygen is a nonmetal, so that bond is actually an ionic bond, and what we're looking at is Na plus and O minus. That minus charge means that we are looking at a strong, which suggests the 2-type or our bimolecular mechanisms. So if we go back and look at what our substrate said substitution. We now have a second piece of evidence suggesting that we are running an SN2 mechanism. Okay? Last thing that we could piece together if we really wanted to was looking at the methanol. That is our solvent. And you'll notice that this solvent is polar protic. Protic because we have the HO bond of our CH3 structure. That gives us the protic name. Which is misleading because we would look at a polar protic solvent and say we're running a 1-type mechanism, not a 2-type. Remember, leave the solvent for dead last because the solvent can be misleading. In this case, it is extremely misleading. So, based on the substrate and our nucleophile, we're running an SN2 reaction, which means we need to do backside attack. So I will bust out my red arrow showing my curved arrow for the mechanism. kind of clean some of this stuff up a little bit here. We're going to take the electrons from my negatively charged oxygen, and those are going to come in from the back side of that carbon-bromine bond and force the leaving group to leave. Okay? The result of this, I'm going to regret drawing it in the box, so I'm not going to draw it in the box yet, because that would be what I'll enter into sapling. So what I'll do is first draw it in a secondary section. So this is my sketch of product, if we want. Okay. In the sketch of the product, what I'm going to do is try and maintain all the original bond angles that are in my starting material. So there's my deuterium, there's my hydrogen, the bromine left, and then I would have a new bond to my OCH3. Okay, and if we went through and added in our lone pair electrons, our bromine left as our purple bromine. It left as a negative charge because it picked up the electron density. Our oxygen shared one pair of electrons, making that new bond, and we now have our product. Okay? As I'm sure Isaac in the back of our classroom is now saying, those bond angles look horrible, you're a horrible artist. That's true, I am. So let's fix that. That's why we go through and sketch out our product first. Remember, in the case, or in this situation, we've now butted up the electron density of all of those groups. So that means those atoms are going to push up away from the electron density of our nucleophile, which means we would better able to draw the structure probably along these lines, where here's our OCH3, and what happened to our wedge and our dash? Okay, well, all that happened is we pushed them upwards. We did not exchange their positions. Our wedge is still hydrogen and our dash is still deuterium. And now what we have is our final answer for our overall structure. Depending on what the sapling question was, I don't know if they asked for lone pairs, but we might need to add those. Okay. Before we click submit, we might review again what happens in this overall reaction. We would expect an inversion in stereochemistry. So if we invert, if we started with R, we'd end up with S, and S, we'd end up with R. So let's go through and check with our starting material. I'll go through and show it in orange. Bromine would be 1, carbon would be 2. Our deuterium ends up being 3 because it has a heavier atomic mass than our hydrogen, which is 4. I could go through and flip this structure over, but I'm kind of lazy. I'm going to go through and say we're going to connect 1 to 2 to 3, which is going in the the counterclockwise fashion, which would be S. But because my hydrogen is wedged, I'm looking at this structure backwards, which means this conformation is S. If we go through and take a look at my product, I'm now going to go through and do the same idea. My oxygen is number 1, my carbon is number 2, my deuterium is number 3, my hydrogen is 4. Go through and run our sequences from 1 to 2, 2 to 3. That would suggest that we are running let me go back to that previous one. I don't know my clockwise. So let's go back to our starting material. Let me try that again. It's late. Give me a break, I guess. 1 to 2, 2 to 3. We're running which direction? We're running counterclockwise, which would suggest S. But because the hydrogen is aimed at us, we're going to have to exchange that to R. So our conformation for our starting material is R. If we go through and look at our product, we're running from 1 to 2, 2 to 3, which is R, but again our hydrogen is aimed the wrong direction. To assign R and S, our lowest priority must be aimed away from us. So that means we would switch it to our S. What happened? We started with R, we moved to S, we've done an inversion of stereochemistry, everything is perfect, we submit into sapling, and hopefully we get our answer correct. One thing to note now that there's so many different colors floating on this, the sketched product, which I'll box again in red, what I drew out in this sketch would probably not get credit in sapling. Okay, why not? Well, as Isaac complained about earlier, the bond angles are drawn horribly. Sapling is very nitpicky about getting those bond angles and those and arrows and all of that stuff drawn in the appropriate fashion, and it's for multiple reasons. The primary reason is that it needs to be correct. We should show it as it would be three-dimensional. The secondary reason, sapling has to be able to grade these assignments. It's grading it by assigning particular thresholds for where individual bonds are allowed to be. If you don't have your bonds put in those particular threshold arrangements, it will mark it as wrong. So if we drew in my sketched product, you would probably not get credit. If you draw in the official product that I put in my black box, that should get you credit. Okay? So hopefully that helps you out. If it doesn't, let me know, send me another email, and I will try and set you up with another video. Okay? Thanks for your question. If you got more, send me an email, let me know, and I will try and put a video together. Thanks.